Welcome to Scrap Paper and Philosophy 18. Today we're going to read from the Red Book. I believe there's a pun intended here because I haven't read all of the Red Book, but we're going to read part of it. And the name is Partial Differential Equations, an Introduction by Walter Strauss. And we begin by noticing that all of physics has been summarized in Chapter 1 using 8 lines of applied mathematics. Now, what really caught my eye here, there's a pun that's not so intended there, but what really caught my eye was the 8th equation, which says quantum mechanics. Now, this is a simplified version of the Schrödinger equation, because the full Schrödinger equation, instead of a uxx there, which is the second derivative with respect to the spatial dimension x of the wave, you see that second derivative there, uxx. In the actual Schrödinger equation, it's written like, look at number 4, Laplace's equation. Think of this as uxx plus uyy plus uzz. So the sum of the three spatial, the sum of the 3 second spatial derivatives. Think of that expression not as equal to 0, but think of that expression as replacing this uxx here. And then you have the entire Schrödinger equation missing only one thing, which would be a forcing energy, an energy term that's forcing some additional behavior of the wave. But if there's no forcing energy, and in a hydrogen atom there will be, and Mr. Strauss is going to solve the entire hydrogen atom for us, or actually he's going to describe the solution for us, but in such a way that it's an astounding solution that really shows us, the hydrogen atom as far as quantum mechanics goes. So there's a hidden subtext here, that the theory behind imaginary numbers, the harmonic functions, the complex variables, Fourier series, all of that is motivated by number 4, which is Laplace's equation. And Instead, we decided to explicitly put an I here, which is something that sounds a little bit absurd as a modeling hypothesis. It makes the equation way less tractable in terms of sums of partial derivatives, let me put it that way. So, I sort of begin to suspect that I equal to the square root of -1 is not the full story. Maybe the square root of -1 is really 1 with a 50% chance of being 1, times -1 with a 50% chance of being -1. But I haven't personally used that modeling hypothesis. What I'm going to do here is I'm going to celebrate this 8th equation for us by solving it numerically over about five or six Planck lengths. I hate that word, Planck length. Planck length, Planck length, Planck length. Oh, Planck lengths. Okay, the length of one Planck unit. We see this is written in 2 dimensions, which is 1 dimension of time, ut, and one dimension of space, uxx, it's the second derivative of the wave with respect to space here. So this is a dispersion of the wave. If you have differences between, well, I'm not going to worry about that now, because you'll see everything I'm talking about in just a second. But what I am going to do, I guess, is get myself some coffee, because I don't think I'm going to be able to do this without coffee. So I'll be back in 1 second. Okay, so as a warm-up, I want you to look at the function u equals e raised to the ix. And what you will notice about this function is that it's the solution to an ordinary differential equation, not a partial differential equation. And I've indicated the ordinary differential equation there. And it's, in a way, it's already starting to look like the Schrodinger equation, because the only thing that's missing between that, which the function u equals e to the ix solves, and that other equation, which we call the Schrodinger equation, well, in one dimension, the only thing that's missing is a partial derivative with respect to time instead of the function u, and the I in front of the uxx. If we were doing this in one dimension of space and then the other dimension of time, that's the only thing that equation is missing. So what I was saying there is that look at this boxed equation right here. Make this u into a u sub t, that's the time derivative of u. Put a negative I in front of this u sub xx, that's the second derivative of u with respect to x. And then this equation, whose solution is u equals e to the ix, is the Schrodinger equation in one dimension as written by Dr. Strauss. But before I solve that equation numerically, I want to really stress this function u equals e to the ix, because what I'm going to show you, in a sense, is that we've been taught to think. What I'm going to tell you is that the Fourier series is, in a sense, a mirage of Cartesian coordinates. But before we get there, let me show you what we did with the x-axis. We yanked out the x-axis from the center of the circle. We yanked out the x-axis. We called it 0. We yanked out the entire x-axis as if it was a string. And then we wrapped the string around, starting with the center of the x-axis at this point, and then perhaps the positive direction that way and the negative direction that way. And that way, we trapped our motion in this circular motion. And that circular motion is not going to propagate out in space, unlike the intuition that the Fourier series gives us. And I'll show you what I mean here, okay? Here, I show you that the signal u corresponds exactly to the height here in the circle. But once the signal u completes a complete cycle, a complete wavelength, well, then the signal u is back where it started, and it's not really moving in space. It's only moving in time, because what's moving in space is a circular motion. For example, a diameter spinning. Okay, that's the only thing that's moving in space, because the signal u is really only moving in time. The signal u, it cannot propagate in space, except we've been taught that it can by the Fourier series. Well, any transformation you do to this function u, replacing x by 2x, well, that's just going to make it go twice as fast. Or like make two sums, or just take e raised to the ix and sum it to e raised to the ix. Then you get 2e raised to the ix, and that's what I'm showing. Maybe I should. Okay. So that's that, and then that's that. Then that's that. It's the same motion of u except twice the height or magnitude. That's what you get for trying to run two circles at the same time. Two unit circles at the same time. And down here is the only way you're going to get any displacement in space. Let me show you. You don't start here. At this point, if you have a phase shift, for example, replace the x by an x plus phi or theta. Well, that looks like phi. I know theta is the fat symbol, and this is the, I don't know. But anyway, this just gets to be second nature, where you've seen this before and you automatically write it, right? But this is important because the Fourier series is going to make us believe that signals like this can propagate out into space, and they can't. What we can do is delay the signal, say that now we don't start here anymore, now we're going to start here, and then we add a signal to that. And that signal that we add, so let's say we start here, and then we start spinning like this. You see, we start here, and now we can spin away somewhere out in space, because that's what the delay will cause. And as we spin out here out into space, then we can have another delayed signal telling us to spin somewhere else in space. But if you don't have the phase shift, you are never going to displace in space. The building blocks here are really displacing only in time. So that said, let me move on to numerical solution of here's what we're solving numerically. So here's the equation, equals 0. I think I did this wrong. I think it was a negative I there. Yeah, it was a negative I. So ut is really I times uxx. But I think I did it right in the computations, so that's okay. And then we have the quantum wave in one dimension, which is, I'm sorry, this was a quantum wave in one dimension. And then if we just take out, and then if we just solve for this, ut plus uxx equals 0, we're going to have just a simple wave in one dimension. And why don't we do that first? So here's my simple wave in one dimension. Here's the initial condition up here. Remember, this is an entire dimension, so we're imagining that this continues somewhere else with other numbers, which may or may not be 0. And in this case, if we are really going to imagine that each of these little numbers represents a Planck length, then you know that the other numbers cannot all be 0, because the square of the norm has to integrate to 1, And in order to get this thing here to integrate to 1 using all zeros and using a single 1, we would have to divide that 1 by the square root of a Planck length. And then the integral is 1. But we didn't do that. So we're just assuming that, somewhere else there's going to be other numbers. And then here's what u sub x is. We moved from 0 to 0, so we moved 0. Here we moved from 0 to 1, so we moved 1. Here we moved from 1 to 0, so we moved -1. Here we moved from 0 to 0, so we moved 0. And then the u sub xx, it's the same thing as the u sub x. Here we moved from 0 to 1, so we moved 1. Here we moved from 1 to -1, so we moved -2. Here we moved from -1 to 0, so we have to add a 1 to that to ensure that we moved from -1 to 0. And then when we're calculating the next, then when we're calculating this, ut equals, well, this expression, u sub t, is how much we have to change the value of u in time. And the instruction is change it by u sub xx. And I did this, and here I did this wrong. I put a negative, and it should be a positive, but here I did it right. I think I added. So here I changed the initial value 0 by a u sub xx of 1, and I got 1. Here I changed the initial value 1 by a u sub xx of -2, and I got -1. And here I changed the 0 by a u sub xx of 1, and I got 1. And then if I repeat this process for the next time, then you see that we're going to have a triangular structure of numbers just expanding outwards. And the edges of this triangle are all going to be equal to 1, right there. And I mean, not the edges, but these two edges of the triangle are all going to be 1, and then I mean a side, excuse me, and then this side of the triangle is all going to be these numbers there, and by some miracle, all these numbers are going to sum up to 1. Same here, 1 minus 1 plus 1 still sums up to 1, exactly like the initial sum that you got there. But what we really wanted to show finally was you can see why I've been procrastinating this. My goodness. So, same deal here. We got the 1, the -1, and the 1 for u sub xx. But then we had to multiply by I before adding. So so 1 times I is I, plus 0 is I. -2 times I is -2I, plus 1 is 1 minus 2I. And 1, right there, 1, this 1 times I is I, plus 0, it's going to be I. And here we have the same deal. We have this triangular structure, except it's leaving in its wake on this side here. It's leaving complex numbers, and on the edges, we no longer have the constant number 1 on the sides. Excuse me, on these two sides, which are not the base. So if we call this side on the bottom the base, and these two the other sides are going to be completely symmetric. But instead of having a constant 1, we're going to have a 1 here, and then we're going to have an I here, and then we're going to have a -1 here. And then I made a mistake, but I actually corrected the mistake enough to be able to complete this process. And on u of time t plus 3, we're going to have a -I. And then on u of time t plus 4, we're going to have a 1. So it goes 1, I, -I, it goes 1, I, -1, -I, 1. Here it's going to go 1, I, -1, And I haven't done the work because I messed up, but it's going to go then negative I and then back to 1. And then I'm not going to do all the work, but a computer can do this, and I believe it's going to repeat back 1 I. Again, what this is just the unit circle 1 I, negative 1, and negative I, just like rolling here. And it's rolling with the correct sign. And here we have a unit circle that's also rolling, but it's rolling with the wrong convention. It's rolling with the opposite convention of a positive sign that we did on this other side. Maybe you can see that, maybe you can't. Not a big deal, maybe. So I think I'm going to maybe pause the video. I mean, conclude this video. Let me see if you. Well, I guess I'll conclude this video. See you later. Thanks for watching. Last thing I wanted to show you is that I made a mistake last time, and I'm going to let Dr. Strauss correct me. This is the hydrogen atom, and it's written using the mass of the electron. This is the mass of the electron right there. So if we were writing a wave for the hydrogen atom, I suppose it's really a wave for the outer shell of the hydrogen atom, because I don't see the mass of the proton there. But anyway, I stand corrected, because this is what the probability of finding mass in the region is. It's not it's not the integral of the complex conjugate. It's the integral of the norm squared. Thank you. Oh, by the way, that integral, we know that it equals 1. So that's what that spiel was about, having to normalize that number 1 there to a 1 over the square root of the Planck length. It's because if we don't do that, we don't get the integral in 1 dimension to equal 1 when we're doing this in 1 dimension. And so, okay, thanks for watching. I'll leave you with a homemade clip. I hope you enjoy it. Thanks.